go on. First of all, I will load R. I will go to my R portable directory. Okay. I show every time how to load R and R commander, so you don't have excuses at exam. Load package, R commander. Takes a while. I change the working directory. If you don't change the working directory and at exam it gets stuck while you're navigating through your directory while saving your file, don't complain. I set it not to my desktop, but to have a directory called R. Okay. Very well. Now I load my workspace. The workspace will contain sleep questionnaire. I don't have it here, as you can see. Load workspace, sleep questionnaire. Okay. I set it as an active data set. Since I've loaded it from the console and not from inside our commander has not realized that there is a new data set, so I have to set it. Okay. Just take a quick look. Yes, it's it. Okay. Let's see. Let's switch to two variables. First case is a nominal and a nominal variable. Okay, what to do in this case? Well, in this case, the standard choice is the famous contingency table. A contingency table is just a cross table. The ones of you who have experience with Excel for sure have seen the pivot table. Okay, let's see whether on the web we find some examples of contingency table. Contingency table. Okay, you can see here clearly a contingency table. Okay, you just have the two nominal variable, in this case event observed yes no, events forecasted yes no, and you have how many yes yes, how many yes no, how many no yes, how many no no. Okay, in a contingency table having just the numbers doesn't tell you so much. It's much better to have also the percentage, but let's see a practical example. Okay, so where are contingency tables? Statistics summary contingency table two-way table. Statistic contingency table, not statistic summaries. Okay. Two-way table. Okay, you choose your two variable, the one which goes on the row and the one which goes on the column. For example, on the row we take sex, which is a typical nominal variable. On the column we take whether the marital status. Okay. For the moment, no percentage, and we also remove the chi-square test, something we'll talk about much later. Okay, so we just get the numbers. Okay, and here you get. Unfortunately, honestly, the graphics of R, it's very bad. Okay, but you can understand that you have female 27 single, 101 married, 15 divorced, and 7 widow. Male 27 single, 87 married, 6 divorced, and 1 widow. What? Okay. So what does this tell us? Well, it tells us that there are 27 female single, 101 female married, 15 female divorced, and 7 female widow. On the other hand, there is only 1 male widow. So it's pretty evident that the number of male widow is much less than the number of female widow. And this, I think, there is no discussion. However, it's not so clear whether the number of married men is less than the number of married women. Well, the absolute number, yes, but don't forget that the total number of men is evidently less than the total number of women. Okay? So this 87 may be the 60% of total men, and this 101 may be the 60% of total women. Okay, so this number, this 87 may be less than 101 because there are less men, not because the men marry less, or sample, obviously. Okay, so in order to solve this issue, we cannot rely simply on numbers. We have to get the percentages. Okay, so we have to get how much this 87 is compared to the total men. Okay, and how much this 101 is compared to the total female. When you want to get the percentage compared to the total of the row, you have to ask for row percentages. Okay, pay attention, because as I write here, it's very easy to mix, ask for column percentage when you need row percentage and vice versa. So I want to know how much this 87 is compared to the total number of men. So compared to the row total, so I have to ask for row percentages. So row percentages. Okay, I re-get the numbers, and then row percent. Can you see that the sum on the row is exactly 100? Okay, so the 87 was 71% of the men in our sample, while 101 was 67% of the female in our sample. So the percentage show us a completely different thing. Show us that in our sample we have slightly more married men than married women. Okay, we have less divorced men than divorced women. We have much less widow men than widow women, and we have more single man than single woman. Okay, so usually in a contingency table, usually always having the numbers is meaningless unless you have exactly the same number of female and the same number of male. Okay, what is much interesting are the percentages. Sometimes the row percentages are the interesting ones, other times the column percentages. It depends on the situation. Okay, well, if for example you want to know in all married people sample how many of the married people are women and how many of the married people are men, in this case you want to get to know the percentages in the vertical direction, because of the married people you want to know how many of them are female and how many of them are male, and in this case you have to ask for column percentages. So now you know that of the entire married people, 46% are male and 53 are female. Well, mostly because the female are more than the male. So in this specific example, these are the meaningful percentages. Honestly, I don't see any good use for the column percentages. Well, let's see another example, because I know that this issue may be hard to understand. Let's see. Ed level by Marishall. Okay. Oops, I have to remove the column percentages. No, not percentages. Okay. So we have here one single which has done primary school, one married which has done primary school, 0 divorced with primary school, 1 widow with primary school. Seems as the people who are divorced don't, the people with primary school don't divorce. Okay, while the people who divorce are the one with postgraduate degree. But it may be because these are much more. So again, these numbers don't tell you too much if you don't compare them with how many postgrad do you have, how many undergraduate do you have, how many widow do you have, how many divorce do you have. So again, if you want to get, for example, within all the single people, okay, how is the distribution of third degree titles? In this case, since I'm asking within all the single people, how is the distribution of the degree titles, I will have to ask for column percentages. And now I see that within all the single people, the distribution is 27 postgraduate, 38 undergraduate, 20, blah, 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 blah. Okay? Pay attention that you cannot compare this one with this one. Okay? Because the married people are much more than the single. Okay? Now, if you want to get to know the people with an undergraduate degree, how much do they marry, how much do they stay single, how much do they marry, how much do they divorce, okay, you use the other percentage. So within secondary school, 57 is married, 33 is single, 3 are divorced, 6 are widows. Okay, so depending on what is your issue, you may want per column percentage and row percentages. I have never seen a case in which it's useful to have total percentages. Never seen. Okay, so this is the contingency table. It's more or less the frequencies, but for two variables crossed together. Okay. Graphs. When you have two variables, the traditional graph is this one, without any doubt. Okay. It's the number of apps. What is this? Average session frequency per month of smartphone usage by operating system. Okay. So iPhone, Android, iPhone, Android, iPhone, Android, etc., etc., etc. So you have two variables here: entertainment, genre, lifestyle, news, social networking. So the activity and the type of operating system. Okay, and you can represent them in this way. Okay, to compare activity by activity and one operating system with the other one. Okay, you can have also them staked. So same thing, but you take the red bar and you put it above. Staked has the advantage that you can get an idea of the sum. Well, in this case, maybe the sum is not interesting, but in this case, it's the cost of patents. European, US, and Japanese patent cost. Okay, so you have the validation fees, transaction costs, and procedural fees. Well, for example, you can see clearly that to get an Apple 13, you have a lot of transaction costs. Okay, while Apple 6 has the same procedure fees, but much less transition costs. Okay, so and you get also the total. So staked, it's useful only whenever you can get total. This is one of the few cases in which three-dimensional may, I say may, be good. Okay, for example, the same as here, but in a three-dimensional version. Well, still some columns are covered, so honestly, it's even better still better this one, but this one may be good. Okay. And this one, on the other hand, it's a rare example, probably the only one I have ever seen, of a useful staked area chart. So this is an area chart like this one. Where is it? Like this one, which here was totally meaningless. Here instead, it makes sense because here you have time, so it makes sense to have continuous lines instead of bars. Okay, and thanks to the area, you can see how much, for example, Android not only is what is this one? Average session frequency per month has a high average session frequency. Okay, but how much? No, this is global smartphone shipment by platform. How much Android is shipping today? But how much has it shipped in total during its existence? Because it's the area which is highlighted here. So while iOS, you can see that in total it hasn't shipped so much, but we may maintain a constant, almost regular shipment. What is this one? Symbian is going to die, obviously. BlackBerry is slowly going to die. And Microsoft Windows is going to, now it's 2013, now it will be much larger. Okay, so this is one of the rare examples in which a staked area chart is useful, but honestly, usually I remain with this one and sometimes with this one. Let's see what can we do for in R. Nothing. As far as I know, there is no variable graph for a nominal versus nominal. Okay. Well, just to use this slide, I have put here the suggestion how to export your graphics into Word, but we have already done it last time. So just right click on the graphics and copy it as bitmap. Okay, so if you want to get some graphs for these cases, you have to put the data into Excel. Okay, let's go to descriptive statistics, scale versus nominal. So you have a scale variable and a nominal variable. Imagine, for example, age and sex. Classical. Okay, let's go. Statistics, summaries, numerical summaries, age. Okay. Here you click summarize by groups. Summarize by groups. And you summarize by sex. It means that you will get the numerical summaries of age divided by female subject and male subject. Subject with not a variable sex will be skipped. Okay, so same thing as the summary statistic mean, standard deviation. You can see that the mean of male is slightly smaller than the mean of female. We are always talking here in our sample. Okay, so it's slightly smaller in our sample. We will see later how can we extend the results that we get for a sample. For example, here that the average age of male is slightly smaller than the average age of female, which in the entire population I think it's true. How to extend it to the entire population. But for the moment, it's only in our sample. So this means descriptive. Descriptive means that we are only describing our sample. Standard deviation, interquartile range. So from 18 to 35, male has an interquartile range shorter from 19 to 31. Blah, blah, blah. How many data? You can see we have much more female than male. And we have a lot of age. This is whenever age is not a variable. Okay, so pretty easy. You can compare them. Usually you compare the mean and that's all. You don't compare any other thing. Maybe the median, 44 against 43.5. Okay, let's see table of statistics. Oops. Statistics, summaries, where's table of statistics. Factors, or you can pick more than one. For you stick with sex, response variable, age. Okay, let's stay with the mean. Okay, it's exactly this thing here, but you just see it in a different way. So nothing extraordinary. The only advantage that you can get only that one and not all the rest. Okay. The other advantage here is that you can have more than one factor, so more than one nominal variable. We'll see later when we'll talk about nominal variables. Okay. And what about graphs? Well, graphs are more or less the same thing. We use the graphs for the scale variables and we apply it by groups. So we use histogram by groups. Obviously, histogram by groups must be one above the other so that you can clearly see how the distribution is different. And boxplot by groups, which must be obviously one next to the other. Okay. These in particular are the boxplot of daily log returns at Nasdaq 2012 for different companies. So there are log returns for some different companies. You can see this one has a much less variability, okay, and this much more. So this one is more risky, we say in finance. This one less. You can see the median is almost zero for all of them. So what you earn is more or less the same. This one you risk less. This one you risk more. Okay. Here, this is the height of female 200 students, male 200 students. Male students are obviously slightly higher. Okay, you can see it's a classical normal distribution, but it is not so classical. Okay, to histogram, you must put them one above the other in scale, so you don't have to shift this one, otherwise you will not see the difference. 70 above the 70, 68 above the 68. Okay, it's in inches. Okay, how can you do it? Well, R has only one feature. You cannot display this thing here in R, but you can do this. Box plot by groups. Graphs. Where is the box plot? Box plot. Again, age. Plot by groups. Sex. Okay, but no other option. And you get, oh, the median is almost the same. Male have a higher variability. Well, strange. Strange, it's age, it's not height, sorry, it's age. Okay, let's do it with height. Boxplot. We have height, yes. Oh, here, male are evidently 180, these are tall people. 164 for female. Well, it's too much according to my opinion. A median of 180, so about 50% of the population is above 180. Okay, you can call out the box plot as usual. How can you do it? Well, you take the last instruction and you add comma call equals c, and you have to remember your palette. Let's see whether I can remember it. So we have female, which is traditionally is magenta. So 1, 2, 3, 4, 5, 6, and 4. So 6 and 4. I think that you can also write between quotation blue and pink, but let's try later. So submit. Yes. Let's try writing instead of 6 pink. Let's see. Oh, it works. Okay. And if we write here instead of 4, 0, I don't think it will have also 0. That is wonderful. Okay, so you can also, if you don't remember your palette, you can also explicitly say the column names in this way. Okay. Okay, nothing else, unfortunately, so no histogram. And finally, what happens when you have a scale and a scale? So first of all, the descriptive statistics. The descriptive statistic is the traditional correlation matrix. Okay. Well, matrix. Matrix is a huge name because you can do it also for more than 2 variables. But when you have 2 variables, it's the correlation number. Okay. We have 2 types of correlation, the Pearson and the Spearman. Okay. The Pearson linear correlation goes between -1 and 1 and tells you whether the values, and I repeat the values, of first variables are related linearly to the values of second variable. Okay. If it is +1, it means they are perfectly linearly related. When the second variable increases, the first variable increases proportionally. Okay. When the second variable decreases, the first variable decreases proportionally. When it's -1, it means that they are perfectly negatively linearly correlated. When first variable increases, second variable decreases proportionally, and vice versa. When it's 0, it means that it's more or less random. When first variable increases, second variable doesn't care, sometimes increases, sometimes decreases. Okay. Sometimes doesn't do anything. Okay. Spearman, on the other hand, it's exactly the same, but instead of looking at the values, it looks at the relative position. So puts all the people in order, doesn't matter the number they have. For example, if you're talking about age, it doesn't matter whether the oldest one is 85 or 97. The oldest one is the oldest one, the last one. Okay? And the first one doesn't matter whether it's 3 years old or 23. The last one, the youngest one is the first one. Okay? So converts all your values into 1, 2, 3, into a ranking system. Okay, for both variable, and looks at the ranking. Well, it has the big advantage that if you have strong outliers, for example, when having to deal with income is a typical variable which has a huge outliers, so people who earn really a lot and a lot of people who earn much less, let's say, in the average area. So when you have to work with outliers, the Spearman kills the outliers, so kills the effect of the outliers. While if you use the Pearson correlation and you have big outliers, the Pearson correlation will be strongly influenced by them. So depending on whether you want to be influenced by your big or extremely small outliers or not. Okay, because the Pearson takes into consideration the values themselves. The Spearman only the order. From a certain point of view, the Spearman converts your scale variable into an ordinal variable before doing all the calculation. Okay, let's see. So we have, well, the traditional height with weight. So statistic. Where is it? Where is it? Correlation matrix. Height and weight. I have to keep control pressed, okay, to select both. Okay, I choose Pearson. Well, it's silly that it displays a matrix, but height with height obviously have a correlation of 1. Okay. Also weight with weight. Okay. Height with weight have a correlation of 0.56. It means that when height is increased by 1, weight increases by not by 1. Weight feels only 56% of this effect. Okay. Let's see the Spearman, whether it's strongly different or not. I bet not so much. $61. So it means that there are some outliers here which disturbs the correlation. Probably it's the person who's extremely fat, even though not being so tall, it disturbs the correlation. This person has the effect slightly reduced in the Spearman. Okay, let's see other things. For example, age with height. Usually old people are slightly shorter. Let's see. Height, not with weight, but with age. Pearson. Minus 0.0096. So very, it's practically 0. It means that there is no correlation, at least in our sample. Okay, let's see the Spearman. Almost 0 also the Spearman. It's slightly positive. Please, in your thesis, if you have a result like this one, it's not positive. Okay, as I hear in the news, whenever the stock market makes plus 0.000001%, it's positive. No, it's 0. Okay, so a result like this one is 0, and also a result like this one is 0. Okay. Okay. I don't go into the details deeply, the difference between a Pearson and a Spearman correlation. If you really want to know them, well, take a course in statistics, or Wikipedia is usually your best friend. The statistical part of Wikipedia, according to my opinion, it's done perfectly. Okay, which graphs do we have? The traditional graph, the scatterplot. Okay. In fact, now we will build a scatterplot of height. Oh, sweet. Scatterplot. I recommend the graph scatterplot. Graph. Where is scatterplot? And now it's scatterplot. It's not scatter anymore. A scatterplot. Okay. So x traditionally as x variable, you take the ones which is not influenced by the other one. Okay. So usually you can't do anything about your height. Your height is determined by your genetic and by usually how much what do you eat exactly when you were young. But you can do a lot with your weight. Your weight depends on your height. Okay. So traditionally height on the x because it is not influenced by weight, and weight which is influenced by height on the y. It's not mandatory, but okay. Why? What is this mess? This mess is because I have not done remove all unnecessary options. I don't understand why the scatterplot has 300,000 unnecessary options. Okay, options. Ta 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 ta. Okay. Oh, the scatterplot. Let's see. Height, weight. Okay. So you can see that there is a relation because here people which are above 185 tend to weigh more than 60. Okay, otherwise, they will die soon. Okay, and people who are shorter than 160, with one exception, tends to weigh maximum 80 kilograms, and they are already rather large. Okay, with two outliers, this one and this one, which are also marked with her ID number. Okay, when you use Spearman correlation, this person will not be marked as a person weighing 160 kilograms. Will be simply marked as the fattest person. So it will be simply put after this one. Okay. So the huge distance that there is here will not be considered. Okay. So this is what I mean with the difference between calculating the Spearman correlation and the Pearson correlation. Okay, same thing for this one. This one, the huge difference in centimeters here will be, this person will be practically put here. Okay. Okay, you can see that there is an evident correlation, even though slightly, because you can imagine a line going up. Okay, just as an exercise, I copy it as bitmap and I put it inside Word. Op, done. In case you plan to resize it, it's a better idea to do it before, because if you resize it later, as you can see, you don't see anything. Okay, so it's a good idea to put it of the right sides before. Okay, let's see the last one, age versus height. Scatterplot. So here, what do we put? We put height on the vertical one, because it depends on age, and age on the horizontal one. I remove all the necessary options. Well, I don't see any relation, honestly. It's just a cloud of points scattered around. It's called scatter because usually the result is this one. Okay, with this person, very old. Also here, when you do Pearson correlation, this person, despite being much older, 12 years older than this one, will be put here. So just older than this one. This person is almost 2 meters. Okay. Let's see whether we can do other graphs of two-scale variable. Well, you have the mathematical graph. Honestly, the mathematical graph is exactly a scatter plot. But there is one big difference. The big difference is that your x variable is put in order. It's put in order in such a way that you can connect the points with a line, okay, and have a mathematical graph, the ones that you used to have at high school. Okay, here it's absorbed photon flux density by net photon synthesis. Okay. Okay, so remember, practically it's a scatter plot, but the values of the x variables, first of all, must not be repeated. So if you have a value for 100, you cannot have another value for 100. Okay? And then they must be put in order, so R can connect the points. Okay, let's see how to do it. Well, just copy this, just type this instruction. I know that for the moment they don't mean anything to you, but this one, submit. It means that you are building a variable outside your data set x containing values from -20 to 30. And now we build also this one. It means that you are building another variable y, which is x squared minus 3x plus 1. It's a parable. You have studied it at high school. Okay, so now we have two variables. One is x, which is -20, -19, -18, -70, blah, 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 blah. And one is y, which is some numbers. We want to plot x on the x-axis and y on the y-axis. Okay, we have now this x and this y, and we would like now to plot them on a line graph. The graphs, line graph. But unfortunately, you can search as much as you want, you will not find x and y. Why? Well, because they are not inside our data set. We have created them in this way and they are not inside this data set. So please don't worry what I'm writing now. Copy it, new data set equal data.frame. Okay, so I'm creating a new data set with X and Y. Okay, let's see. First of all, I change it. New data set. Take a look at it. Can I take a look at it? No, I can't. Can I edit it? Okay, at least editing I can. Okay, yes, contains X and Y. Yes. Okay, I look at it. No, it's not possible. Okay, now that inside the dataset, I can use the line graph. Well, it's a pity that you cannot take things from outside the line graph, but the data set. However, okay, X, Y. Okay. Unfortunately, for the moment, there are only dots, but the connecting line, it's this horrible symbol. Let's see whether we can get a better symbol as connecting line. No, there are no options. This is the only alternative that you can have. Finally, the last graph which is suited for true scale variable, it's this one, honestly. It's a scatter plot, but with a regression line. It's something that you will learn in the statistical courses. It is, for the moment, not part of this course. Okay. Now, what happens when you have three variables? Well, you probably will not believe me, but you can build contingency tables. So you can build a contingency table with three variables. It will be a cube, so something three-dimensional. How can you display it? Well, obviously it will be displayed layer by layer. Okay. So one of the variables will be used to split the table into several different, the cube in several different tables, and the other two variables will be represented in each table. So a little chaotic to see it. Many people like it, however, I don't. Let's try. Yes, I have to go back to the other data set. Okay. Multi-way table. For example, sex by ed level by Marichal. 3, 2, 1. So sex will be on the row, educational level on the column, and Marichal will be a variable which splits into different tables. So you will see you have a table for single people, a table for married, a table for divorced, and a table for widow, which doesn't contain too many people. Okay, so this is the contingency table split. Okay, when you have three scale variables, well, you can still use the correlation, but it will not be the correlation of all the three, but 2 by 2, obviously. So it's 3, but honestly, so statistics, correlation metrics, age, for example, height, I must keep control pressed, and weight. So I take three variables, I click OK. So you can see it's not age by height by weight, but it's age by height, age by weight, height by age, height by weight, etc., etc. So each couple will have its own correlation. Let's pause a little bit. I can't put it to pause. Okay, now let's go on. Graphs for three variables. Well, the traditional one for three scale variables, it's the surface plot, something like this. Something which, at least in our commander, is not possible to do. Okay. There are many more interesting graphs. The best one I've seen is this one, look. It's available on the web. Allora. it has loaded. Okay, you can see here you have represented income per person, one variable, life expectancy, second variable. Okay. Then the size of the circle are countries. The size of the circle, it's the total population, so three variables. So you have three scale variables representing the same graph. So the bubble chart, I think it's a very good idea because you are able to represent three variables on the same chart. In this specific chart, also other variables are represented. The color represents the continent. You can see people from Africa, from Central and South Africa, countries from Central and South Africa are all here, okay? While countries from America are here, for example. Okay? And if you want, you can also click on play, and if it doesn't crash, you can play anything here. It will move, however, from year to year. Probably on your computer it works better. On mine, it doesn't work. Okay, so bubble chart is a nice way to have three variables represented at the same time. Now I'm really tired of this website which doesn't work, and we'll go back. Okay, unfortunately, obviously, R is not able to build things like this. Or when I say it's not able, it means that it's not able using simple things as R commander. Because in R, there are a lot of packages, and I'm pretty sure there is a package for almost everything, if you learn to use it, however. R, on the other hand, can do scatterplot by groups, so two scale and one nominal variable, which is also a rather frequent thing. So, and you can build a scatterplot by groups. Let's see. Okay, graphs, scatterplot. So, for example, age versus alcohol. Okay, plot by groups. We'll have it according to marital status. So we'll have the people who are divorced indicated, or to age level, education level. Where is education level? Age level. Okay, options. Remove all these silly things. Okay, well, how to understand? The X's are people with undergraduate degrees. Oh, there are a lot of people here which are rather old and drink a lot, which are the postgraduate degree. Okay, well, there is one person with secondary school which drinks a lot. The other ones are scattered here. So you can see it's visible, but honestly, it's not the best thing in the world, especially because R insists in using this notation, which is rather old. Now it's much better to use colors, and that's it. Let's see whether we have some interesting options. No, doesn't seem to have interesting. Oh, you can change the point size, but nothing else. Okay, and let's try to change, instead of add level, plot by sex, which has only two things, and so maybe we'll see it better. Oh, this one looks at least more comprehensible. You can see that male and female, with the exception of these two people who drink a lot and are male and female don't change too much, honestly. More or less scatter in the same way. Okay, and we stop here with descriptive statistics.